Hello, everybody. Hello. Hello, everybody. Okay. So let me share my screen. Hello. Hello, everybody. Okay. So let me share my screen. Let me just mute this really quickly because I was hearing myself. Come on. This worked before, so let me get this working really quickly. Okay. Okay, so hello everybody. Welcome to this is my AP Physics 1 or College Physics review. And this is like the ultimate review so we're going to be reviewing everything that we've learned so far up until the final. I'll be going over the textbooks, notes, conceptual questions, actual application questions, past physics tests, and formulas that you would want to have in order to review. So hopefully you guys like my setup today. So let's get started. Okay, so the first unit was, the first unit, it was all about significant figures, what physics is all about, the different, what is a meter, all that crazy stuff. So, or not that crazy, all that boring stuff. So right now, we'll go into the notes behind it. So first, significant figures. So when multiplying or dividing numbers, you would want to take the lowest number of significant figures. You want to have the same amount of significant figures in the answer as the number with the least amount of significant figures. And for adding and subtracting, you would want to take the amount of decimal places to have your final answer. Yeah, you count decimal places, and then the amount of decimal places is your final answer. So let's say that you have 16.1 plus, 4. That would be equal to 20.1. But for the decimal places, we would want to count the least amount of decimal places. So it would be 20. I'm pretty sure about that. Sorry, this was like a long time ago. And then and then for example, so we would count something that has like 22.3. This would be equal to 3 significant figures. And then a number that is like 3.0. Everything after that decimal point, that is now a significant figure. So that would be 2 significant figures, etc. And then, so basics, which is that order of magnitude in power is of 10. So for instance, if we want to put something in scientific notation, like let's say a 3 that goes on, for 6 decimal places, that would be 3.0 times 10 to the 6. And then another thing that we'd want to know is that we use length as in meters, time as in seconds, and mass as in kilograms for most of our calculations. And we would use in order to convert some of the basic conversions that we'd want to do in order to actually, let's say if we forgot the actual specific numerator converter in the test, we would have to do, I forget exactly what it was called right now. It was like, anyways, it was basically what you did this sort of math in order to get the right answer and convert. So let's say that you have 62 seconds and you would want to convert that to a minute. So that's 62 seconds over 1 times 60 seconds are in 1 minute. So you want to cancel out the unit that you do not want, and then you want to include the units that you're solving for. So this would be like, cancels out. So it'd be something small. Sorry, I cannot do math right now in my head, but it would be something very small. And then let me just clear this. Okay. And then, that's basically it for unit 1 in the notes section. So I can go on to the conceptual questions that we want to go into really quickly, and then we can go into some more actual problems. But for right now, so for example, if we want to know the current definition of a standard meter of length, you would want to know that that's based on the speed of light traveled in a vacuum. So length is equal to meter is equal to based on speed of light or velocity of light in vacuum. And then we also want to know that the current definition of standard time is based on the frequency of radiation emitted by cesium atoms. And then the standard kilogram is just based on an object in France. And then other things like a kilometer is less than a mile, stuff like that. And then, oh yeah, also no system of measurement is more accurate than another. It's just based on different quantities that are interchangeable. And then, sorry, I'm looking at something really quickly. Yeah. Okay. So yeah, and then so significant figures, we want to remind ourselves that when determining the number of significant figures in a number, zeros to the left of the decimal, which are like right here. And let's say, like, oh, I guess that wouldn't be 1, it would be like that. So that 0, let me get to my pointer. That 0 right there, that is going to be counted in our significant figure calculation. Okay, and then let me look at the actual textbook and then talk about what the first unit was all about. Yeah, so converting units is going to be on the test. So yeah, a lot of this stuff you're probably not going to have on your final, as it's, what a model is, a theory, a law. But this is useful, especially the significant figures part and other things like trigonometry and sine and, not triangulation. That's a little bit much, but yeah. And then estimating. Excuse me. If you want to estimate for a triangle, and then you say you don't want to use trigonometry or you forgot a calculator or something like that, we all know how you can, if you have two similar triangles, you can always do something like a ratio where side A over side B is then equal to side C over side D. I mean, side D over side C. So that would be A over B is equal to D over C. Okay. And then I think, yeah, this first unit is pretty easy. Yeah, you want to include sig figures in your answers on your test. That's always a big thing, so make sure to watch out for that. Okay, now the first big topic that we're going to talk about is kinematic equations in specifically one direction. So kinematics is how objects move, and dynamics is why objects move, and that's not going to be discussed in this course, but it will be discussed later on. So it's good to make that difference. That difference. So we're going to be talking about translational motion, so movement without rotation right now, and we'll add that in on unit 8. And then this is in so you need to have reference frames, direction, and units in order to calculate these. So for instance, a reference frame could be, let's have a train going at 60 meters a second. And then let's say if you're standing looking at the train from this direction, you'd see that the train is moving 60 meters a second. 60 meters a second in this direction. But let's say instead of standing there, you're now standing here and you're going 60 meters a second this way. Now your reference frame would be right here. And then because the train is moving at you 60 meters a second and you're moving at the train 60 meters a second, that means that the reference frame of the speed that the train is going at you is now 120 meters a second. So that is why reference frames are so important, especially with Newton's laws. Okay, so yeah, so you want average speed. So this is, you probably already know this, but this is another formula that you might want to know. So average speed is just the average. So the distance traveled over time, and average velocity is the displacement over time. So velocity has direction, while speed is the magnitude of velocity. So for instance, velocity is just, speed is just the absolute value of velocity. And then, so if you're in calc-based physics, you're probably not going to be watching this, but in order to get the instantaneous velocity, you would take the limit or the derivative as a change in, you would take the derivative of the, what's it called? You would take the derivative of the position versus time function, but we're not going to be talking about that for this course. So now into the most useful formulas for this. We have 4 of them. So the first one is velocity final equals velocity initial plus acceleration times time. The second is change in your x or y is equal to velocity initial plus time plus 1/2 acceleration times time squared. The third is velocity final squared is equal to velocity initial squared plus 2 times acceleration times change in your x or y, whichever you're solving for. But remember, if you're solving for x or you're solving for y, you have to make sure that your velocities are in the x and y direction too. And then finally, we have a very easy one, which is average velocity is equal to velocity final plus a velocity initial over 2. And then, so also, if you're finding something like, you might be asked to do this on your final, but area under a velocity versus time graph is going to be the total displacement. So velocity versus time, let's say that your velocity increases, does not increase at all, then it goes down. I'll actually review these right after I'm finished explaining this, the different velocity versus time, acceleration versus time, and position versus time graphs. So the area under this, under the line, that is going to be equal to your displacement. But however, since we're not in a calculus-based course, we're not going to be doing that as much, but we can do that for simple shapes. So now into the different types of graphs, the kinematic graphs. So we have a simple position versus time graph, and the position is going to be in the x direction. So let's say that we have something that is increasing, so its speed is continually changing. That could be, so if you have taken calculus, you'll know that the tangent line slope is increasing, showing that the next graph, the velocity graph, is going to be increasing at a constant rate, which is the velocity versus time graph. And then finally, from this, we can get its acceleration versus time graph. And this is just going to be a positive constant. So as you can see, as it's increasing in speed, it's increasing its velocity. It's not just having a constant velocity. If it did have a constant velocity, then there would be no acceleration, and we cannot make an acceleration versus time graph, as acceleration would just be that t-axis, which is 0. Okay. Yeah. So let's continue to look right here. So now we've explained the major components. And then for all of these, it's important that you memorize these formulas, the 4 formulas I've shown, which I can put back on screen now, because these formulas are useful they're like critical for all of our future calculations that we might need. Even for, as we'll eventually see in Unit 8, we have rotational motion, which uses these variables, but it uses the same formula, but not these variables. Okay, so now we're going to go into, apart from things like braking distances and stuff like that, we can also have free fall. Free fall is the easiest type of kinematics because it only involves one type of acceleration, and then that is in the down direction towards Earth. So acceleration is always downwards. So when we get, let's say we have a problem that a ball is dropped down from a 50-meter high building, So we have basically everything that we need already. And then we want to find the velocity that it has when it reaches the bottom. We would just use one of the formulas. So we can just have V final is equal to 0 plus negative 9.81 meters a second times time. Except in order to find time, we have to actually get the change in height. So we can use another formula. So that would be negative 50 meters is equal to, and I am referring back to this formula. And then if you want to have a calculator, because for this formula, we would have to use something like it was the formula with x is equal to negative b plus or minus the square root b squared minus 4ac all over 2a. And that's really important for that one. So a calculator makes it much simpler and faster. So we can now find that now. So we have 0 times time plus 1/2 acceleration, negative 9.81 times time squared. So you solve for time, put that into time here, and then you can have your answer. Except this is super simple, so I'm not going to spend a lot of time going over this. Let's see. Yeah. Okay, and then we'll move on to unit 3, which is the same thing, but kinematics in two dimensions. So let me see if we should do any conceptual questions for unit 2, chapter 2. Oh yeah, I have one already. This one is a very confusing question, but I'll try to explain it for you guys right now. Okay, so you have a racing car that accelerates uniformly from rest along a track. So we have a track and my crudely drawn car, and then it accelerates. So we know that has acceleration. And then we can just draw x is this direction, and then y is nothing going to happen because, we're only in one direction so far. So the track has markers spaced at equal distances along from the start, as shown in our figure. So marker 1 and marker 2. These are congruent. So the car reaches a speed of 140 kilometers an hour as it passes marker 2. So 1, 2. Oh, wait. I am 1, 2. So the car reaches 140 kilometers an hour as it reaches this. Where on the track was the car when it was traveling half the speed at 70 kilometers an hour? So I'll let you guys think for really quickly. Where do you think? Is it going to be at marker 1, between marker 1 and 2, so this region, or before marker 1? And then the answer is actually before marker 1. So this is because as acceleration increases, let's look at the graphs again. So if it has a constant acceleration, that means, yeah, that is not right. That's non-constant acceleration. So for acceleration, it needs constant velocity. That means that the velocity is constantly increasing. Now, what we see in the position versus time graph is that if velocity is constantly increasing, the position or the amount of distance that it travels is constantly increasing per time. That means that as it's increasing in speed, it's covering more and more distance faster and faster. So when it's moving at 70 kilometers an hour, it has not traveled that far because it's still, even though it has the same amount of acceleration, it builds on it and it keeps on going faster and it travels more distance faster and faster. So meaning that it reaches 70 kilometers an hour before marker 1. And we can go into the math behind it, but this is just a conceptual question, so you want to get this immediately. So it reaches 70 kilometers an hour right here, and it keeps on building up in speed. So that would mean that it could be it would reach 70 kilometers an hour, then 80 right here, 90, 100, 120, it just keeps on. That's really bad. So it just increases exponentially. So yeah, so acceleration is always constant. and it's negative. It's always pointing down for free fall. I'm going to look through some more conceptuals. Oh, and then also something that we can look at is velocity, different velocities. So if let's say that we have velocity on our quadrant on our XY axis. So one way that we can determine velocities is by having, let's say, I'm going to make this from the origin and I'll choose a different color. So we can have, so velocity is a vector. So velocity is a vector. So when we're adding up vectors in X and Y planes, that means that they have direction as long as magnitude. This distance, as shown right here, the distance is equal to the magnitude, while the theta, which can be like right here, is equal to the direction. So that means that this is going completely negative in the y direction. So this could be an example of velocity during free fall. So when you want to add these, you can use the tail to tip method, meaning that when you want to add velocities, you can, let's say we want to add a velocity that is, we're now right here. If we want to add a velocity, we can do this graphically by adding them like this, where we add them tail to tip, and then measure this new long hypotenuse. And then, or we can also do it a different way. So if we want to do the same equation, we can divide it up into the X and Y components and then add them there. So for instance, let's zoom in on the second one. This second one, we can make this equal to a 90-degree triangle. And if we have the theta, which almost we always do have, or we use trigonometry, we can find the Vy and the Vx components, which we can then divide this up, except this one's only a y component, which can equal our final, by squaring them using Pythagorean theorem. And then this might take a long time, so feel free to skip it to the parts that you'll need. Okay. And then another type that I want to look at is where on a graph, a position versus time graph, where does it show? That is definitely not a position versus time graph. Where, a truck or a car is moving the fastest and the slowest. So time and then position. So let's say that this is moment A, and then this is moment B, this is moment C, and then this is moment D. I know that's a little bit out of order, but so where on this, so if this is tracking a truck's position over time, where would where would the exact moment of time where the truck speed is equal to 0? So we can first find that by finding either we can, try to add a tangential line. And when that tangential line is a constant or equal to 0, that shows us where the object is turning around. Whoa. That shows us where the object is turning around, as its velocity must be 0. So think about it like this. So when you have a car that is accelerating in one direction, well, it has a velocity in one direction and is accelerating the other direction, its velocity will become smaller and smaller and smaller till it's 0, and then it will flip, and then it will become this bigger and bigger and bigger. So that moment when it's flipped, that shows that whenever a velocity is changing direction or turning around, it's going to equal 0, unless it's in 2 dimensions or 3. But for this simple one direction of motion, this point A is where it is equal to 0 and turning around. And then at which moment in time is the speed greatest? So in this one, I drew it a little bit, not exact because I'm drawing it by hand, but we can look at the change. You want to look at the rate of change. And then where the rate of change is highest, it's asking for the speed. So where the rate of change is highest anywhere, the absolute value of that you would want to find. So it looks like D and B are the same, but if it was asking for velocity, we would choose A because that is a higher rate of change, and this is negative. And then also, we really quickly, I'm going to go over 2 other scenarios, and then I'll move on to another unit or do another question. And then so one, if this is velocity graph versus time, velocity versus time graph, and then it shows the speed like this, it just shows that this is showing that this has a constant negative acceleration. So its acceleration versus time graph would be like down here. But it's like when you're looking at just the velocity graph, it shows that the velocity is originally a very high number, except the acceleration or the slope of that is negative, and then it hits 0, so it's not moving, and then it is increasing in speed in the negative direction. So its position versus time graph would look something like it's like increasing but concave down. It stops, hits 0, and then it's going in the other direction. So it looks like an upside down parabola. And then another question that you might see, a misconceptual question, is where when you throw, so a child throws a rock off a bridge, a couple seconds before he throws a rock off the bridge, the same exact bridge, the same exact mass, but that doesn't matter because the force due to gravity is the same, and we're ignoring air resistance. So this has a larger speed because we know that it's already had a longer time falling, and this has a smaller speed. So the answer for this question, which is like what changes between the 2 rocks, the acceleration is the same for the 2 rocks. And then the the rate of velocity. So, the amount of velocity difference between the 2 rocks is going to be the same, but the position difference between the 2 rocks is constantly going to be like different. So what I mean by that is the velocity of this rock could be like 2 meters a second. And then in this rock, sorry, I just had a total like brain fart. And then this rock could be, let's say, 5 meters a second. It would always have the same difference in velocity, but it would have not the same difference in distance covered. And I know that's not right because it would be above 9.81 meters a second. Well, actually, depending on the time between the throw. Okay. Let me see if I have any actual questions now, since we went over the misconceptual questions. Okay. We definitely have a lot, except I will not go through all of these because, this is the easiest unit. Yeah, the graphical motion, we can skip that. Okay, yeah. So one thing that we can look at really quickly is, let me clear my screen. So a ball is thrown vertically upward with a speed of 26.9 meters a second. how high does it rise? And then, so how high does it rise? So we want to find the change in the y. So we would want to pull up the formula, which it can be changed in x or y, is equal to velocity initial times time plus 1/2 at squared. And then we want to find the time. So we don't have the time, right? And then so in order to find the time, we need to use a different equation. And then so that is the v final is equal to v initial plus acceleration times time. V final is going to be 0. V initial is 26.9 plus acceleration times time. That is 9.81. So that is 26.9 divided by negative 9.81. That becomes positive, and that is equal to the time. And then we can just plug that in into here to velocity initial. And then I'll continue it down here. And then the change in y will be equal to 36.9189 meters. So yeah, this unit is extremely easy, which is good. So hopefully you'll have lots of luck with this unit on your test and then bring up your grade. Yeah, so that's it. And then it's for two directions of motion. You just split it into the x and y components, and then you can quickly find the right answer. Okay. Yeah, the tail to tip. Oh, and then one quick thing about the tail to tip is that when you're adding them, you cannot add them tail to tail, because then this resultant velocity is just not going to work. Okay. Yeah, projectile motion is parabolic, which is why you see the initial times time plus 1/2 acceleration times time squared. Let's look at the summary. Yeah, and to find like tangent and stuff, we all know that sine is equal to, whoa, equal to opposite over hypotenuse, stuff like that. Okay, now we're going to move on to Newton's laws of motion dynamics. Okay, so force is equal to Newton's, which is, so force, these sometimes they give you questions on your test, which is the units. So force is equal to mass times acceleration, which is Newton's first law. And then the units for this is, so that is kilograms times meters a second squared, which is equal to Newton's. And then so Newton's first law is every object continues in its state of rest or uniform velocity in a straight line as long as no net force acts upon it. And then so this makes sense. Sorry, this is like the third law. I always get those mixed up. But so this makes sense because if nothing is acting on an object has no force to make it change its velocity, no force to make it change its direction and change its way of motion. So that is pretty simple. And then Newton's second law is that, Newton's second law of motion is the acceleration of an object is directly proportional to the net force acting on it and is inversely proportional to the object's mass. The direction of the acceleration in the direction of the net force acting on the object, but that in word form is equal to force is equal to mass times acceleration. Yeah, that is the second law. And that if nothing is moving, then that is equal to, if nothing is happening, the net force is equal to 0. Because there's no acceleration, right? And then, oh yeah, and then so the third law is every action has an equal and opposite reaction. So let's just say for the force of a ball on the ground is equal to the negative of the force of the ground on the ball. And then, oh yeah, and then a conceptual question that tricks a lot of students is how when you have something on a table, like a box, the box has a force of gravity and the table has a force of normal up to actually push the box off the ground. I mean, to keep the box from phasing through the table. Except these are not action and reaction pairs. It might seem so, but these are not. The actual action reaction pair is there's a force of normal prime on the floor, and then that is the action reaction pair. These are not equal. Well, they're equal and opposite, but they're not action and reaction pairs because they're on two different objects, not on the same object. And then, yeah, so you're going to see a lot of elevator problems in this unit, such as like when you're, an elevator's in constant motion, so velocity is equal constant upwards or downwards. Velocity is constant. Your weight is going to be equal to your weight on the floor. So weight does not change. But let's say velocity, you're accelerating upwards. Let's say you're accelerating upwards 1/2 of gravity. So you're accelerating upwards. This means that your weight is going to be like increased. It's going to be increased by that amount that you're accelerating. So for this, your weight would equal 3/2 of gravity, because not only are you feeling the acceleration of 9.81 meters a second on your body, you're now feeling acceleration upwards. And then in order for your body, in order for your weight to feel that, you would get them added together. And then lastly, if you're accelerating down by 1/2 gravity, then your weight would be equal to 1/2 gravity. And then, let me check this. This right here. Okay. Newton laws of motion. Yeah, Newton's first law is the law of inertia. Yeah. And then, so we can look quickly at another problem you're going to see, which is, so you want to create free body diagrams, so you just draw a point and then you draw all the forces acting on it. So for this problem, it's on a table. We have a mass of 12 kilograms tied to a mass of 10 kilograms, which is being pulled by 40 newtons of force. So what we can decide from this is that the force of friction, the force of friction is equal to mu k or mu s, which is the coefficient of static or kinetic friction times the force of the normal. And then, so the tension in this force is equal to 40 newtons, and then tension 2 is equal to, we're not sure yet, but we can immediately know that it's less than 40 newtons, as this tension force only has to pull this mass instead of pulling both of these masses. Okay, and then so the max amount of force required inhibits motion if it's too much. So we can calculate that. So I did not fully look at this problem and it did not give us a coefficient of static friction. But let's say that like the coefficient of static friction was 0.8. And then so we can find both this, we can add up the masses. So that is 22 kilograms. 22 kilograms times 9.8, 1 times 0.8. And then that is equal to, let's just multiply that by 10. So that's 220 times 0.8. And that is definitely more than 40 newtons, I can say. So that is greater than 40 newtons. So from this would not move. And then if we had less static friction and less kinetic friction, then it would move. And then it's good to know that the force and tension is less. So we would need to find, if we actually did have movement in the system, we would find the acceleration of the system as a whole. And then from that, we can find the tension force that is equal to right here from the force of friction that is being, if it's like, moving in constant velocity. I mean, yeah, if it's accelerating, we can find the entire system. And then let me get my red pen. So the acceleration of the term system, we find the force being subtracted by friction, the force being pulled, and then we can have the mass and the acceleration. And if it's moving at a constant acceleration, we can just find, the constant velocity, we can just find the force of friction, which is equal to the tension 2, and then at least for that block, but as a whole, the force of friction for the entire system is equal to that. And then yeah. Okay, let's look at chapter 4. Wait, no, are we on chapter 4? Yes, sorry. Okay. So now to explain more on that tension. So let me find a good question. So tension. One question that stumped me while I was just learning about this was that if we have a table, 2 pulleys equal to a weight of 1 Newton, and they're attached. What is the tension in the string? And then that tension would be exactly 1 Newton because it is equal to the tension being pulled up from either side. It would make sense that would be 2 newtons because it's pulling the entire thing, but it's because they're the exact same. The amount of force that is in them, it's completely distributed throughout. So the 1 Newton of tension is on either side, but it's, equal right here. So we can kind of draw on like those lines, if that helps you think about it. And then sorry, this is like my first time going over, so I'm trying to like figure out how to do everything in the most efficient way possible. Oh yeah, and then if we have something, like let's say that we have a scenario, like we have a table with a box on it, a pulley, and then some heavy weight down here. So if this is accelerating downward, we know that it's accelerating downward. So that is equal to, so the force of tension up minus the force of gravity down is equal to mass times acceleration. This means that the force of tension is not equal to the force of gravity. That would be true if it was in constant velocity, but because it's accelerating, we know that the force of tension is only equal to mass times acceleration plus the force of gravity. So that means that it will not be equal to the weight of the tension. And a lot of people try to input that, and probably me when I was first doing this too. And then almost always this will have some friction on it that way too. And then, okay. And then let me find some more problems. Okay, so let me get to this problem. So let me find the problem really quickly. Let me just get it on my phone too. Okay, so this problem is probably the hardest problem I've encountered for Newton's laws of motion. So a helicopter, that is a helicopter. Okay, so a helicopter has a bucket that is, or we can call this just a mass, which is equal to 430 kilograms. And it is on a 29.1 meter long cable. And then the helicopter is returning at a constant speed of 27 meters a second. And the theta right here is 36.1 degrees. And then find the horizontal force of air exerted. Find the horizontal force exerted by air resistance on the bucket. So that is the force of air resistance. Well, wait, so the force of, yeah, because the air is pushing onto the bucket this way. So the force, so find the horizontal force exerted by air resistance, okay, on the bucket. So what we first want to do is, of course, we want to divide everything into, its components. So we have the force of tension. This is the biggest force that we're going to be looking at for this problem. So that is the force of tension, cosine theta, and then the cosine is the adjacent over hypotenuse. So that would be this is equal to force of tension, y, equal to, which is force times gravity of the bucket. And then this simplifies into mass times gravity is equal to force of tangent cosine theta. And then now we're also looking for, I should just call that y, and then the x. So this is force of tangent sine theta. I mean, not tangent, force of tension sine theta is equal to Ft of x, which is equal to force of air resistance. So that is equal to force of air resistance is equal to force of tension sine theta. So now we want to find the force of air. So one thing that we can do, which is a cool trick, is to divide these two. So that is mass times gravity over force of air is equal to force of tension cosine theta over force of tension sine theta. And then as you can see, that cancels out, and we completely just have force of air is equal to mass times gravity tangent cosine, tangent theta. And then once we have this, we can just plug in and solve. So that would be force of air is equal to 430 kilograms times 9.81 times the tangent of 36.1. And then the force of air is equal to 3,072.9 newtons, which is quite a bit, but it is a big bucket that weighs 430 kilograms. So that is a cool trick that allows you to almost bypass everything and just divide by tangent and multiply by mass times gravity. Okay, and that's like, if you understand that, you can pretty much understand the entire thing, along with, we can look at one inclined plane problem. Okay, so a block is at rest on the incline shown in the figure. The coefficients of static and kinetic friction are U of S is equal to 0.73 and mu of k is equal to 0.62. The acceleration due to gravity is 9.8 meters a second squared, 49 kilograms. What is the frictional force acting on the 49 kilogram mass? So what we're looking at is, so we can, force of gravity is pulling down, and we can divide that into its x and y components. So that would be equal to, so we have this component and we have this component, which is the component of force gravity perpendicular to the normal force. So once we have that, and we can just shift that over here just to make it look nice, because it's, we can do that because it's tail to tip. Since we have that, we can find, so the theta here is equal to the theta here. And then that is equal to, the thetas are equal to there. And then, so this is cosine. So cosine's here, and then this is sine. And then what's the frictional force acting on the 49 kilogram mass? So, it says it's 32 degrees. So this is 32 degrees. So we want to find the force of normal. So that would be 49 kilograms times 9.81 times, that is equal to, wait, let me just fix this really quickly. So the sine of theta, and that is equal to sine of 32, which is equal to, so sine of theta. So opposite of our hypotenuse, the opposite is just equal to the thing that we're finding for, so we can put that x over the hypotenuse, which is mass times gravity. Mass times gravity. Whoa. 49 times 9.8. And then let me get a calculator really quickly. Hopefully I don't run out of time on this thing. Also, make sure you're in degree mode. That always is terrible when that happens. I mean, when you're not in degree mode. Okay, so this means that this section right here, let me just have this yellow. The yellow is equal to 254.727 newtons. So that is the normal force. And then we can really quickly find the cosine, which is that same thing, but just with cosine. $407.648 newtons. Okay, so let me just check something really quickly. Oh yeah, so we know that the frictional force, so we know that the normal force is 254.727 newtons. And then the amount of force that's pulling it in this direction, we can calculate that by doing the static friction. So 254.7 times the coefficient of static, 0.73. Okay, and then sorry, I'm like still sniffly from when I got the flu. And then, so what is the frictional force? So we can just find that by assuming that it's in equilibrium and it's not moving anywhere. That means that the force pulling it is equal to the force pulling it down. Wait, did I do this right? Yeah, so the force pulling it down is equal to 254.7 254.467 newtons, which is a little bit different from my answer, but that is the force pulling it down. And since it's in static, and since it has static friction on it, since it's not moving, it's just equal. The force is just equal to this right now. Okay. So now on to Newton's second law. Yeah, it's the same stuff. Oh my goodness. Okay, and then so now we're on to uniform circular motion. Except let me make sure that I don't have anything else I want to talk about. Yeah, uniform circular motion. Okay, so uniform circular motion, or uniform CM, this is with a constant radius, so just circles. And then so constant speed, instantaneous velocity is always tangent to the circle. So if we look at a circle and it's moving, it always has acceleration inward when something is moving with speed in the circle. And then so that's its tangential speed. And then it goes around the circle, and if it breaks, let's say it breaks right here, it would fly off. It would fly off right here in this trajectory. So velocity changes in direction, not magnitude. And then since velocity continuously changes in direction, that is the reason for this acceleration, as it moves out, but then it moves back in. Moves out, back in, moves out, back in, moves out, back in. And then so in here, you can see the acceleration is always inward. So the force of centrifugal acceleration, so the force, tying this back to Newton's law, the force for centrifugal is equal to mass times acceleration of centrifugal, which is also equal to mass is equal to velocity squared over radius. And that is still the same. So tension force is equal to acceleration times centrifugal force. And then fictitious force is feeling of being pulled out of the UCM. That is actually not true. It's just, let's say you're in a car, going around the side at a really high speed. That force that is pulling you out, that's just the force of the door pushing on your body. And then so Newton's law of universal gravitation. This is something that is this is one of the biggest, most useful formulas that you'll need to memorize. So it's the force of gravity is equal to the big G times mass 1 times mass 2 all over r squared, where G is equal to 6.67 times 10 to the negative 11th. So it's very small. And then the units for that is meters squared over kilograms squared. And then it only works for mass points in spherical bodies, as when something is regular shaped, let's say like that, not everything is, the moment of inertia around the object is not the same, meaning that not everything is pulled in by the same amount. So it's not even. Well, it's pulled in by the same amount, but it's not the same distance. And then, objects in orbit experience weightlessness because since they are continuously falling in, like the astronauts in orbit around the Earth, since they're continuously being pulled in by gravity, they're constantly in free fall. So they keep on going out and then dropping back in, going out, dropping back in, going out, dropping back in. And then quickly, another formula that you can write down is that velocity is equal to the square root of big G, mass of the Earth, times your radius, or that can be the mass. You can interchange the mass for whatever planet you're solving for. So this is a good thing to look at. And then I'll highlight these two. Okay. And then the Kepler's laws. Let me get the big physics formulas out. So for the Kepler's laws, one of them is that, let me see it really quickly. So this is like the second one, but actually I'll go for the first one. So the first one is that the path of a planet is an ellipse. So that's like the sun. All planets orbit in an ellipse because it's not like equal. And then, so that's the first one. The second one is that planet's path sweeps out equal area in equal time. So let's draw that same thing again, like an ellipse. Actually, let me draw a better ellipse. So this leg, for the same amount of time, as it gets closer to the sun, the distance between the sun gets smaller, meaning that it'll cover more distance in a short amount of time, while when it's farther away from the sun, the distance from the sun is longer, but it will cover less distance on the radius. On the circumference. So an equal amount of time, these two, the distances like inside will be equal. And then 3, the ratio of periods squared is equal to the mean distance of cubes squared. So mean distance of cubes squared. Cubed. And then you don't really find a lot of use for that in normal physics. Well, in like example problems and stuff. So I have a lot of different formulas that I can write down right now. So one is that acceleration of radial is equal to velocity squared over r. Velocity is equal to 2 pi radius over your period. Your period can be equal to mv squared divided by r. Linear speed is your arc length divided by time. Angular speed is your theta, your change in theta divided by time. Mass times velocity squared over r is equal to mass times velocity squared over r is equal to mass times gravity. And then those are the most major formulas. And then let me just look at any other things. Okay. And then, so and then okay, let me look for the conceptual questions. Is this the right one? Oh, wait. Okay. So one is 2 small objects with masses m and m are originally a distance r apart. The gravitational force on each one has a magnitude F from Newton's laws equal and opposite. And then the second object has its mass changed to 2m in the new scenario. And the distance is changed to r over 4. And what is the new magnitude of the new gravitational force? So we can quickly find this by using one of the formulas. Let me get my formula sheet. Where did I put that? Okay, so because the radius of this, so if we look back to the formula, let me find it really quickly. Is it? Yeah. So force due to gravity, mass 1 over force due to gravity is equal to gravity, big G times mass 1 times mass 2 over little r squared. So because the little r is being squared, it is over 16, and then 2 on the top, and then 2m, m. And then so this is equal to 2 m over r times 16 over 1, which is equal to 32. So it's 32 times the force. Because this gets squared and it's on the top, so it will become extraordinarily bigger. So a satellite encircles Mars at a distance above its surface equal to 3 times the radius of Mars. If gm, so let me draw this real quickly. So if gm is acceleration due to gravity, so wait, sorry, a satellite encircles Mars at a distance above its surface equal to 3 times the radius of Mars. So radius 3 times the radius of Mars. So r. If gm is the acceleration due to gravity at the surface of Mars, or acceleration due to gravity at the location of the satellite. So that will be, so since the gm on the surface is right here, that would be equal to the force due to gravity. And then when we look at the satellite's force out here, we calculate our force, but with all of these. So that is 4r. So we go back to that equation. That's super useful. Wait, is it square? No, it's not. Mass 1, mass 2 over 4r squared. So we don't really look at that. And then that is equal to, because all of those are the same, when we compare to the other one, which is g mass 1, mass 2 over r squared, it cancels out and then is equal to 1 over 16 times the gravity of Mars when you're far away versus at the surface. So the force, the gravitational acceleration constant would be 1/16 from where it's at the surface. So let's look at a problem. Okay, and then we can move on after this. So it's just really important to make sure you know all of these formulas, because you can often use formulas from a different unit to find your answer. So let's look at this question. So, oh wait, that was supposed to be dotted line. So dotted line, 1.9 meters, a mass of 6.2 kilograms. It has a velocity or angular velocity that way. And then so this is 26 degrees, 9.8 meters a second downward. So what's the speed of the ball when it's in circular motion? So does it tell us the velocity? Small metal balls. Let me read this again. Okay, let me just quickly check this. Sorry about the sniffling again. Okay, so you'd find, so let's just draw this out. So first you'd find the force due to gravity on the object, and then you can find the distance from the center it is that would like fall down into. So you can find where it would fall down to, and then you would, so that's the acceleration inward. And then from that, you can find the tangential velocity from the formula tangential so sorry, I lost my work for this one, so I'm just trying to like explain it to you guys really quickly. So we can review this one later when I find it really quickly, but let me just move on. Okay, so now we're on to work and energy, chapter 6. Sir. After this, I might take a quick break before I finish the review session, and then, so work done by a constant force is defined as distance moved multiplied by component of the force in direction to displacement. So that is equal to work is equal to force times distance. And then for most scenarios, work is equal to force sine theta times distance. So the work net is equal to 1/2 mass times velocity 2 squared minus 1/2 mass times velocity 1 squared. And that is equal to the change in kinetic energy. As if the movement is the if the system does not lose any kinetic energy, that means that it will continue being at the same move, like it'll continue in the same, continue at the same velocity. But if it lost some kinetic energy, that could be portrayed as either that could be potential energy or thermal sound energy and stuff like that. So work is scalar, meaning you can add all work done to get the work net because it is scalar is a number not having a direction. So the potential energy can be elastic potential energy, gravitational potential energy, and the potential energy of gravity is equal to mass times gravity times the change in y. Can be plus or negative depending on the change. So the force of spring is equal to negative kx, and potential energy of the elastic is equal to 1/2 kx squared. And then you can find a lot of different things from this. And then let me just go over the actual work is also equal to joules a second. I mean, that's power. It powers work a second. Wait. So I'm like losing a little bit of brain power right now. Yeah, the work of friction is equal to the change in energy. And then the total energy is equal to kinetic energy. So energy is equal to kinetic energy plus potential energy. And then friction is a force that translates into thermal energy. So you can lose your total mechanical energy of the system. Okay. Let's look at an example problem. Sir. So let's say you have a box up here and you want to calculate how long the distance it takes a stop, the speed at the bottom, and the work due to gravity and work due to force of friction. So let's do the work due to gravity and the work due to force due to friction first. So this is 45 degrees and it's 10 meters up. Okay, so the work due to gravity. So the work due to gravity is the change in height. So work due to gravity is equal to mass times gravity of height final minus mass times gravity height initial. And that is equal to 490.5 joules, as the mass is equal to 5 kilograms. And then for future, the unit of kinetic is equal to 0.3. So that is because, it's just subtracted by 0 minus 0 minus 5 times 9.81 times 10 gives you that. And then so the work due to friction is equal to the force of normal times the mu k, which is equal to sine of 45 times 5 times 9.81 times 0.3, which is equal to negative 147.056 joules. And then, so the work non-conservative is equal to the change in kinetic energy. So that is that. So that means that this negative 147.056 joules of energy that was lost is equal to the change in kinetic energy. So it's the change in actual mechanical energy, sorry. So mechanical energy, that is, so the kinetic energy at the bottom, so 1/2 mass times gravity squared, mass times velocity squared, so 5 times velocity squared plus, which is actually negative because it's, gone down, 5 times 9.81 times 10. And then you'll get the velocity is equal to 11.673 meters a second. And then lastly, in order to find the distance that it will travel, it will be the distance in the stop. It will be, so then you find the force of friction on the entire distance. So that is equal to the full component of normal, since it's not on an incline now. So that would just be 5 times 9.81 times 0.3. And then that is equal to the force of friction. So, and then so you find the total. So you want to find, so the force of, so work is equal to force times distance. So you have this work is equal to the change in kinetic energy again. So of all forces, so that will be this force 5 times 9.81 times 0.3 times the distance x is equal to the initial 1/2 5 times the distance, times the speed, which what I said was, it was like 11.673. Okay, and then that should get your distance. That would be the force times over how long it's acting versus the initial time. And then, minus, that's the initial, and then the final 0, because velocity has stopped. Okay. So let me look at another question. 5,900 seconds. Okay, we can do a quick circular motion one again. Because I did not do the last question because I did not have the answer. So I didn't want to, do something wrong and then tell you guys, teach you guys the wrong thing. That would be no bueno for the final. So that's R. So the mass, and then that's the H. Okay, so we want to find the mass of the planet. So what we can do is how we have the circular orbit. So the satellite is in a circular orbit, which is equal to 5.50 times 10 to the 5 meters. So that is above the surface, which is quite a bit of meters. And then the diameter of the planet is 9.6 times 10 to the 6 meters. Okay, 1.6 times 10 to the 6 meters. And then, so the period is 500. It's equal to 5,900 seconds. Okay, mass of the satellite, sorry, 1.22 times 10 to the 4th kilograms. And then, okay, so the diameter, we want to find the diameter because that is this distance plus the h is equal to the total r, which we want to find. So once we have that, which that would just be half of this diameter plus this, which that will go on the bottom of that entire big equation. So firstly, we want to find the velocity. So velocity is equal to 2 pi times radius. So the total r, which is again, if you take that divided by 2 plus the circular orbit, is equal to 5,350,000 divided by the time t, which is 5,900 seconds. And then if you think about this, 2 pi r over t, this 2 pi r is the 0, pi, and then back to 2 pi. So that is 360 degrees. And then 2 pi r is the circumference. So that's really finding the distance it travels in radians over the amount of seconds. So once we get that, once we find the velocity, which is equal to 5,697.47 meters a second, we equal that to 5,697.47. We equal that to, because as we remember, this formula, which is the square root of g times mass of the planet we're looking for over r. That is equal to square root g, which is that incredibly small number, which is 6.6 times 10 to the negative 11th power times mass, which we're looking for, over 5,350,000 meters. Solve that, and the mass you get is equal to 2.6037 times 10 to the 24th kilograms, which is really big, almost as big as Joe Mama. Wow, that was actually really bad. And then, yeah. So we have found the mass of the planet along with easily calculating the velocity. Okay. I'll try to hasten this up because it is getting a little bit long, guys. So I'm sorry about that. So work. Okay, I'll just move on to the next sections and I'll try to talk to you guys about it. And then I'll think of any examples to tell you guys if I think of any. Okay. So Work non-conservative, yeah. So yeah, power is joules a second. And if, remember, things all start on the same height, then it's going to, if things all start on the same height, they're going to have the same speed when they get down. If they're the same, mass and they're same types. Okay, so linear momentum, I'll try to hurry this up. So linear momentum. So linear momentum is mass times velocity, which is equal to P. So linear momentum is equal to that. And then the force, so force, which we can find is equal to, the net force, is equal to change in linear momentum over change in time. And then the change in linear momentum is equal to the change, the impulse given. So that is equal, so force is equal to impulse divided by time. And that makes sense, as if the momentum is changed by amount, that change in velocity is then equal to acceleration over time is equal to the force. Because mass times acceleration and then divided by time. So, and then we have the conservation of momentum. So momentum is always conserved in elastic collisions. While some of it can be lost and translated into heat or other things like that, it still is going to stay the same because the heat still is energy. So that is the momentum before is equal to the momentum after. So like mass times velocity times mass times velocity 2, mass times velocity plus mass times velocity 2. And that's just prime to signal before and after. And then impulse is equal to force times time. So yeah, that change in P is equal to the impulse. So impulse, and then yeah, that change in P is equal to force times time. Force times change in time. And then that impulse is delivered. So let's just think about that really quickly. So if we want to close our door and our door is open and we have a mound of clay and we have a bouncy ball, would we rather want to throw the bouncy ball to close the door or throw the ball of clay? So when I first thought of this thing, when I thought of the ball of clay, when it would hit the door, stick to it. And then I thought that would be a better it would better transmit the force because it would stick to it and then therefore carry along its momentum. But that's not necessarily true because the change in momentum would be from the velocity of the ball, from the thing of clay, to sticking with the door, and then the door would shut with a velocity that is less than the initial. So the change in momentum would be, the impulse given to the thing would just be enough to slow it down, but not change it to zero. While if we threw a very high bounce, a very bouncy ball, when it would hit the door and then bounce off, that means that the impulse is 2 times because, it changes this plus into a negative, a negative. So that would be double the amount of impulse. So change in B. So since it's double, that means that the force on it is exerted more because since the force exerted that way is double, as we look back from here, the force change in impulse, so impulse divided by time, that would be more this way and then equal and opposite reaction. So it goes that way more. And then, so when we have elastic, that means that everything is saved. So I have a very nifty formula sheet right now. So elastic is kinetic energy can be used. So that means that kinetic energy before 1/2 mass times velocity squared equals the kinetic energy after. So no kinetic energy is lost. But for inelastic, that means that some elastic kinetic energy is lost. And then you cannot fully use you cannot use the kinetic energy formula. And then, but when it says that something is completely inelastic, it means that it sticks together. So let's say that we have, so like something that would be completely elastic is that, let's say we have no friction and we have billiard balls. So billiard balls, so one hits one. And then, so that would mean that because one is hitting the other, and then that's before, and then after equals a number. And then so this is equal to 0, and then this is now off. That would be an elastic collision, because since they have the same exact mass, the transfer of kinetic energy would be the exact same before and after. And then we actually do have a formula for that. So a perfect transfer of velocity is just equal to, where's the formula? So, well, actually, the formula is not really anything because it would just be the exact same. Sorry, I had a brain fart again. So when something's completely inelastic, it means that it sticks together. So this means that if we have something like a truck hit a small car, and then if they stick together, let's just say the truck and the car, like they're squares just for easier to draw. If they stick together and continue in the same path, that is a completely inelastic collision. It's just called that. I'm not exactly sure why, but yeah. Okay, and then so if we have the same exact mass for both before and after, we can use an equation. Same exact mass before and after. We can use the equation VA plus VA prime is equal to VB plus VB prime. So this just marks that's very easy to understand because all the masses just cancel out because they're the same. And then like the billiard ball, that's an example of equal masses. So the center of mass, when we're looking at the center of mass for something, that basically it's the mass times the position. So let's say we have, let's take the x0 here, and then we have a long plank. Let's say that we have something right here, and then something big right here. So that's 2m, and then this is m. So let's say this is 2 meters, and this is 4 meters. So when finding the center of mass, you want to take a specific point which is easily known to you, and then you calculate the distance times the mass divided by the mass. So for a quick example, this xcm is equal to 2 times m plus 2m times 4 divided by 3, because it's the mass. So that is equal to like 2 plus 8, so 8 equals 8/3. So it'd be closer to around here. And then it would be right there. Okay. And then, and then really quickly, before I move on to the next unit, when we're looking at, momentum is always conserved for these. So I got this question wrong in my last test, which is, such a stupid mistake, because momentum, I actually put that for inelastic collisions, kinetic energies. I knew that kinetic energy was not conserved for inelastic collisions, but I actually put that momentum was not conserved for inelastic collisions, but momentum is always conserved. So unless when it's like transmitted to like thermal energy or something where it loses a tiny bit of momentum. But usually it's always conserved. So let's really quickly say that we have a ball and it hits something that's stationary. And then after, their velocities look like this. Okay, so what we want to know, what we do know, is that the center of mass still travels along the axis that it was going before. And this works for almost all forms of complicated motion. So the center of mass, in which is, the direction, so the velocity, of the center of mass is equal it's always going to be equal along the same axis that I was showing before. Except now, this is just, we just have to divide this into its x and y components. And the y components, if we write this down, so x must be equal to the same. So the mass times velocity, not center of mass. So velocity 1 plus 0 is equal to, let's call this and this theta 1 and theta 2. So that's 1, that's 2, 2, 1. So, and then velocity 1 prime, velocity 2 prime. Okay, sorry. So, and then so now this would mean that, so the velocity here is equal to the cosine. So mass 1 times the cosine of theta 1 times velocity 1 prime plus mass 2 times minus, because it's in the, no, it's in the right, sorry. Looking at the wrong thing. So mass 2 times the cosine of theta 2 times v2 prime. So this will add up to equal the momentum before. And then now here for the y before, there's no y movement. So it would be 0 is equal to, and then so since there's no y movement, we can easily see and we know that these two sections cancel out. So that will be mass 1 times sine theta 1 times v1 prime minus mass 2 sine theta 2 times v2 prime. And then that would equal 0. And you can easily solve for things there. Okay. So yeah, center of mass, easy stuff like that. Did I go over torque yet? I actually am not sure. Is it in angular rotation? Yeah, okay. So yeah, it's in this one. So moving on to rotational motion. So this is definitely the hardest type of physics for, I would say, almost anyone to understand. Okay, let me get to the. Oh wait, oh yeah, let me get back to that question that I didn't have the answer to before, because now I do have it. So let me get to it. Okay. So the vertical forces is T cosine theta is equal to mass times gravity. And then the horizontal force is T is equal to sine theta. Oh wait, T of sine theta is equal to mass times velocity squared over r, because that is one of our formulas. Okay, so from this, so mass times velocity squared over r, so we can sub in the tension force because we are finding the velocity squared. So T is equal to mass times gravity over cosine theta. So that is mass times gravity times tangent theta is equal to mass times velocity squared over r. Masses cancel out. And then so that is equal to, so the velocity then is equal to, you can plug it in for yourself to find out if you're not sure, because so the radius will then be equal to sine of 26. Yeah, 1.9 times the sine of 26, sorry. And then so the velocity is equal to 1.99527 meters a second. And then the period is the time that it takes for the entire thing to happen. So that is, so 2 pi, we're finding the distance, and then So the distance traveled is 2 pi times the radius. Radius is 1.9 times the sine of theta, which is 26. And then once we have that, so that is the circumference. So that's the distance it travels. And then we're dividing it by the time. By the rate that it's traveling that distance. And then that is equal to seconds. So that is 2.622 seconds. And that is how you do it. So it's actually pretty easy once you know how to do it. And yeah. I just put it in the wrong pile. So that was my bad. Okay, so I did linear momentum. Okay, really quickly, only external forces can change the momentum of the system, while net momentum is conserved. The momenta of individual objects can change. Energy dissipates into sudden heat. Center of mass follows parabolic shapes. So the momentum of the system is equal to mass of the system times velocity. And then, sir. Okay, so now on to chapter 8, which is the most difficult. Okay. So we have, sorry. Let me just open this up. So in a circle, so we have a change in theta. So a change in theta over a change in time is equal to omega, which is angular velocity. Velocity. And then so also this change in theta is equal to the arc length. Well, actually, no, it's not equal to because it's the length, but the length is equal to this arc length that it covers is equal to the radius times theta in radians when it's in radians. And then so a full circumference, as you know, is 2 pi times the radius, and then that's the amount that it is. And then so the angular acceleration, which is alpha, is equal to omega minus omega over change in time. And then, so once we know these basic steps, these basic quantities, we can know that every point on a rotating body has an angular velocity, omega, and a tangential linear velocity, v. So when we look at this, let's draw a circle. Oh my gosh. Se repite. Okay. So we have the center. X is center mass. So if we have point P has a velocity this way. It has a distance this way, and it travels in omega. And it has a velocity. While a point further away has the same omega. Let's call this point D. So point D has the same angular velocity because it covers the same distance. Covers the same angle. But as the angle goes out from the circle, it has to cover more and more distance. So it covers more distance. So it has a higher speed v. So if we want to write this in terms of actual numbers, this velocity is equal to r times omega, the radius times omega. And then the tangential acceleration, which is the acceleration tangent to the circle. So right here, the acceleration tangent is equal to the radius times alpha. And then the centripetal acceleration, which is the acceleration inward, I can draw this on something else if it helps. So the acceleration inward out here is equal to acceleration is equal to AR, acceleration radial or centrifugal. Remember centrifugal because that goes back to the last, excuse me, that goes back to the unit 5, I think, uniform circular motion. And that's equal to omega squared times the radius. And then from here, every point on a radial, on a rotating circle has centrifugal acceleration. So it has centrifugal acceleration, except that changes based on how far out you are. So if you're farther out, remember, so if you're farther out, your velocity is greater. So you're moving farther away faster. So you need to have a bigger you need to have a bigger amount of acceleration pulling you in. So that's why radial acceleration gets bigger the farther you go out based on your radius. And then if angular velocity of a rotating object changes, it has tangential acceleration, which we already talked about. If angular velocity is constant, each point has centrifugal acceleration. So yeah, so rotation without slipping. So right here, rotating motion has two parts. One, where it moves, everything is moving horizontally. At any point you draw is moving horizontally. And the second part, where every point you draw is rotating. Oh my gosh. That moves down, that moves this way, that moves this way, that moves this way, and then it's rotating all around. What? I'm almost done. Okay. Sure. Okay. And then so once it's rotating, that means that these velocities are combined. So that is, so when it's combined, you have 2v on the top, v, and then no v, because this cancels out. Let me get my laser pointer. These cancel out. This has nothing adding to it along this axis. And then this is doubled. So yes. And then so now into torque, which is a very fun part of this unit. So torque is equal to the lever arm times force. And then I can show you what the lever arm is really quickly as a review. So if this is the hinge, and then where your force is being applied, it needs to be perpendicular. It needs to have a perpendicular connection to the hinge. So your lever arm would, in this case, be the length of the door. But however, if you're having something that is like, let's say you're acting on that same door, but your force is now this way. In order to actually connect to the door now, you need to draw through where your force is headed and now connect it perpendicularly to your lever arm. So your lever arm would be smaller now. Sure, please. Okay. So as you can see, the lever arm diminishes when when the lever arm moves from like here to here, the lever arm diminishes, except torque increases with a bigger lever arm. So force is always greater when the force is exerted perpendicularly, sorry. So torque is also equal to mass times radius squared times alpha. Torque is equal to work times the change in theta, and it is equal to the moment of inertia times alpha. And then another important formula is kinetic energy is equal to 1/2 mass times velocity squared of the cm plus 1/2 moment of inertia times omega squared. Okay. Oh yeah, and it's still useful to know that velocity is equal to square root 2 times gravity times h, and velocity is equal to the square root of 10/7 times the gravity times height for a sphere rolling down a hill. Okay, and then so the further mass is distributed along an axis of rotation, the bigger the rotational inertia is, as it takes more force to move it as the lever arm gets bigger. And then so torque does work as it moves through the wheel through the angle, and then angular momentum is equal to, angular momentum. I mean, the change in angular momentum over time is equal to the net torque. So change in angular momentum over time, over change in time. And then angular momentum is equal to moment of inertia times W. I mean, times omega. Okay. And then you can easily remember this because this over time is just equal to that. Okay. And then, oh yeah, and then looking at a real world example really quickly, when you're like, let's say we have an equation of someone's foot on the floor, someone weighs, that is a disgusting foot. But let's say that the lever arm, I mean, so there's a force, there's the ligament pulling up right there. You have the force pushing down. So the weight and then the force normal. So it would be a distance right here, multiplying by, so if you want to find this, you'd find net torque is equal to 0, and then you'd find it would be equal to the force normal. And then if there's additional points with other forces, you can add them in. And then it would just be the net torque is equal to, let's just call this force A minus force B times, and then it would have to be, you would have to find a point to put it on. So if we put it on point A, the lever arm would be 0, so we couldn't find it. So you just want to look at that. Okay. So the right-hand rule. So you also want to remember the right-hand rule when you're going over something. So where omega is going is equal. So you want to wrap around. So these fingers, like the 4 fingers on top, you want to wrap them around the omega. So if omega is, let's say I'm pointing at you guys, and then I point, and then so let's say I have a bike here that's spinning. So it's spinning like this, right? That means that, imagine if this, I'm not sure if it's like flipped where you guys are looking at, but so the screen, it's the omega is coming out towards me. And then when it's coming out of the screen, it's positive. If it's rotating the other way and it's going into the screen or into you guys, it would be negative. Let's see. So, oh yeah, and then also you can find omega is equal to 2 times pi times frequency, and then the frequency is equal to 1 over the time period that it takes. So is the period that it takes. And then so relating it back to the angular acceleration that we did earlier. I mean the constant acceleration that we did earlier. We have these equations, which is omega is final is equal to omega initial plus acceleration times time. Omega final squared is equal to omega initial squared plus 2 alpha times change in theta change in theta is equal to omega initial times time plus 1/2 alpha times tangent, times squared. And then we have just, average omega. Okay. I will. I'm trying. So, and then the average theta is equal to the theta final plus theta initial over 2. And then, yeah. And then, so, yeah. So, and then there's lots of different problems that we can do about this, but let me find one. So this is like an extremely difficult case when we're thinking about moment of inertia problems and stuff like that. But once we review it, if you understand this, you're pretty much good. So we have one mass one, a pulley, but instead of us just ignoring the pulley, we're going to include it in our calculations now. So it has there's no slipping. So the movement of the line across the pulley means that the angular acceleration, alpha, times the radius is equal to the linear acceleration, linear acceleration. So linear acceleration is equal to radius times alpha. So it is, so let's draw, and it's rotating this way. So when it's rotating this way, when you look at your screen, so when you look at your screen, when you're rotating, it points into your screen. So it's going to be negative because it is clockwise. So right now we have, let's draw the force diagram. So for this one, for mass 2, we have the force due to gravity, force of tension, and then acceleration is downward. So, and then the mass 1, we have force due to tension, force due to gravity, which is split into these components. And then, yeah, that's all we have for that one. And then now we can start, and then we need to do the thing for the pulley. And then that is force about cm, axis of rotation is right there. We have force due to tension. And then we have force due to tension, force of tension 1, force of tension 2. And then, so this is rotating this way. So let me show you. This tension is rotating, trying to pull the entire thing down this way. So when we move our hands over it using the right hand rule, we get that this is positive and this is negative, because that's going this way and this is going this way. Okay. And then now that we have that, we know that it's actually going to turn this way, giving us alpha right there. And then, and then we have normal force right here. So torque net about cm is equal to the moment of inertia for cm times alpha. So that is equal to, let me find that really quickly. So that's equal to, so the torque net about cm, so that is equal to force of tension 2 minus force of tension 1 is equal to 1/2 mass times radius, because that is for a circle or a cylinder, times alpha. And then that, this is a little hint, is regular acceleration over radius. And then once we have that, we also have force of tension minus force of friction on the incline. So this is force of tension 1 minus force of friction is minus force of gravity times sine of theta is equal to mass times acceleration. Then we also have force of tension minus mu k, force of normal minus force of gravity sine theta is equal to mass times acceleration. We plug those two together and we get force of tension 1 minus UK mg cosine theta minus mass times mass 1 times gravity sine theta equal to mass times acceleration. Okay, so now that we have that, we can, oh, and then, so let me just highlight really quickly. So we have this major one, and this major one. And then finally, we have the easiest one, mass 2 times gravity minus the force T2 equals mass 2 times acceleration, which is all about what's happening right there. Let's highlight that. Okay. So once we have that, we can just add this and this. And then once we do that, we get force of T2 minus force of T1 is equal to 1/2 mass times acceleration. And then we can plug that in for 1/2 mass times acceleration. We can plug that in for, let me find out where. Oh yeah, so we can plug that in for right where we have it up here. And then so, oh wait, I mean, we already did that, I guess, because if we think about it, this radius cancels out with that radius, and then we're just left with these two. Okay, but once we have that, we're pretty much good to go and we can solve. So that is the hardest type of problem that we're going to be doing. And then it is getting pretty late, so I'll try to wrap this up really quickly. I know I've said that a lot now, but I am trying. So we're now on to static equilibrium. So this is basically about how, so equilibrium, we need the net force is equal to 0 on x and y axis, on all axes, axes, I'm not sure, on everything. And then we also need net torque to be equal to 0. And we need everything to like not move at all. So because when we're doing this, we can find a few things. So so we can find problems like this, where we have a string, we have force due to tension, we have the height of that, we have the force going in, and then we have a big mass that's hanging down right here, and then we have the force down right here. So we can do a lot of things with this. So when the tension is equal to 0, that means that this force, well, when we set the point, if we set the torque about this point right here, that means that this is already 0. And we can calculate this by finding its distance times that force, distance by that force up, and then distance by this force down. And then we can find any torque if we have the stuff. And then we also know that there's no movement going on in the horizontal direction, and there's only 2. So once we find this height, which would be equal to, which would be in proportion to this height, but not like the exact same amount, we can use trigonometry to find the angle, and then therefore get these two. And then Young's modulus. So Young's modulus is the ratio of stress over strain. Stress is equal to force over area, and strain is the change in length over original length. So when we get this, we can find that the Young's modulus is we can get an equation from this. So the Young's modulus is the change in L is equal to 1 over E times force over area, which is strain, times original length. And then if we divided by L, we would get the change in length. And then, yeah, so this would be equal to, so that is equal to E, which is equal to Young's modulus. And then so that's equal to E. And then that's the formula that we can use. And then that is useful for all types, not just strings. That gives us our amount that it can, stretch and stuff like that. And then we also know that for equilibrium, there exists a stable, unstable, and neutral equilibrium. So for a stable equilibrium, objects return to their initial position. Like, let's say that a ball, right, there would be in stable equilibrium because when it moved, it would go back. But in unstable equilibrium, it would be like something like in unstable equilibrium, it would be something like when a pencil is standing up and then it falls down. Because it's unstable because, sorry, let me find, it moves away from the axis. It does not stay in its original position. And then if the object remains in a new position, it will be in neutral equilibrium, but you don't really see that often. And then another thing that you're going to be seeing is the Bulk's modulus. And the Bulk's modulus is equal to the change in pressure over the change in volume over the original volume. So something with a very low Bulk's modulus is going to have a very high change in volume, which means that it will be very low. Let me check that really quickly. This is unit 9. Unit 9. So Bulk's modulus. Let me just find it really quickly. Oh yeah, which of the following would be expected to have the smallest Bulk modulus? So helium vapor would have the smallest Bulk's modulus, while something like steel would have a very high Bulk's modulus because it would not change its volume that much, because the change in volume would be super low. And then, so, okay, from there, I pretty much went over everything. And then now onto our last unit. Sorry, I'm kind of like having to hurry it up because I don't want to get too long. We've already been 2 hours. So now onto fluids. So in fluids, there's, hello, Lola. That's my dog. So in fluids, we have something like Bernoulli's principle. So except I'll get that to it in a little bit later. But first we have density. Density is mass over volume, as you guys know. And then so what we can get from this is we can have specific gravity. So specific gravity is an object's density over the density of water at 4 degrees Celsius, which is just 1,000 kilograms over meters cubed. So, and then it would be density of object. And then so once you have that, you can also find stuff such as the force of buoyancy. The force of buoyancy is equal to mass of the fluid times gravity, which is equal to the density of the fluid times the volume of the volume of the water displaced times gravity, as the mass times volume. The volume would cancel out and give you mass, but that's usually what we use. And then pressure is equal to force over area. And then so the change in pressure, so pressure, flickered, sorry. So pressure is, so also the change in pressure is equal to pressure times gravity times the change in height of the fluid. So like for a column of water, the higher it goes up, the more pressure would be exerted down. So, and then on to Pascal's principle. Actually, first we should do gauge pressure. So for gauge pressure, the pressure total is equal to the pressure of the atmosphere plus the so the pressure of the gauge plus pressure of the gauge plus absolute. And then absolute is, like the earth pushing down on what you're testing, and the gauge is the pressure at the site, at the specific location. So like for a submarine, this is the, little submarine with this little fins back. Maybe it's a fish because it looks a lot like a fish. So it'd be the pressure from the atmosphere plus the pressure from the gauge down there. And then finally on to Pascal's principle. Pascal's principle basically says that the pressure of an area for an incompressible fluid, an incompressible fluid. So let's say the pressure here would need to be equal to the pressure outputted here. So because the force, because the area is small here, a small force here would mean that since the pressure has to be same here, the force, and since there's a bigger area, the force would increase in magnitude, allowing for a small force to be translated into a big force that's going to push up something of much heavier size. And then so so the Archimedes principle allows you to find the weight of objects, such as, let's say, something that's submerged. So if something is submerged, we have, its force buoyancy, which is the amount of water that basically it takes out, like the force of the weight of the water that's placed, the force up on it, and then the mass times gravity down. So the force would be equal to the mass times gravity minus force of buoyancy. And then you could just find the and then you would find the mass times gravity. So you could find the force of buoyancy, which is density of the fluid times volume of the place times gravity, and then you can find mass times gravity of the object, and then the force, the resultant force. And and then now on to Bernoulli's principle. Oh wait, no, actually we're going to do, I think this is called the equation of continuity. So in the equation of continuity, it basically means that it's kind of similar to the Pascal's principle, but not for hydraulics. It's basically saying that the density, and then this goes for air. So for air, the density times the cross-sectional area times velocity 1 is equal to the density 2 times the area, cross-sectional area 2 times the velocity 2. And then so that basically allows for, that's for air because air is compressible. But for fluids, since they're not compressible, the density is known to stay the same. So we would get area 1, velocity 1 is equal to area 2, velocity 2. Now from this, we go on to the Bernoulli's equation, which is for air, like lift and stuff like that. So the Bernoulli's equation is pressure 2 plus 1/2 density times velocity 2 squared plus by density times gravity times height is equal to the same thing, but on this side. And then that allows you to find lift because the Bernoulli's equation allows, well, the person who discovered it. So like, let's say that this is an airplane wing and not like a chicken leg, which it looks like. So an airplane wing. So it has higher pressure on the bottom. So because let's say an air particle was split into two, it would have to travel a longer distance on top than it would on the bottom, meaning that there would be low pressure on the top and high pressure on the bottom. giving a lift force to bring the plane upwards. And this is how like things fly. So when there's a high pressure zone, and I mean a low pressure zone, once it rushes air to fill it in, creating lift. And then, oh yeah, so the force of viscosity is equal to this variable times cross-sectional area times velocity over the length. And then we also have surface tension, which is this pretty variable, which is equal to force over its length. And then that is for surface tension, gamma. Yeah, so this is gamma. Yeah, and then yeah, I think we've talked about everything. So sorry if I went a little bit faster or something, guys, for this. I know I didn't go fast because I definitely took a long time, but I tried to go over everything. And I try to explain everything well with some conceptual questions for each and some practice problems for each. So I hope you guys enjoyed this, and I hope this helped you guys in some way. If you guys want, I can come out with another episode tomorrow that goes a little bit into depth into more specific areas that we can talk about, such as more rotational problems, more torque problems and stuff like that. But I hope you guys enjoyed this video, and I'm sorry if it took a long time, but I tried, guys. So thank you, and I hope you guys are doing well. Hopefully you guys do well in your finals, and yeah, stay safe and keep on learning.